There are several methods available for service grounding at poles. Firstly, the driven ground rod is a common method. A copper-clad or galvanized steel rod is driven vertically into the ground. Removing this type of ground rod can be difficult, often requiring excavation equipment. Secondly, a ground clamp on a buried water pipe can be used. If a metal water pipe is available and buried at least 24 inches deep, a ground clamp can be attached to it. It's important to ensure that the pipe is continuous and maintains good electrical contact with the ground. Thirdly, a buried ground plate can be implemented. A copper or galvanized steel plate is buried at least 12 inches deep in the ground. The service grounding conductor should be connected to the plate using an exothermic weld or another approved method. Fourthly, the grounding ring is another option. A copper or galvanized steel ring is buried around the pole base to a depth of at least 18 inches and a distance of 3 feet away from the pole. The service grounding conductor should be connected to the ring at multiple points. Fifthly, a concrete encased electrode, often referred to as CE, can be utilized. A steel electrode is embedded in concrete during the installation of the pole base. The service grounding conductor is then connected to this electrode. Sixthly, a driven pipe electrode is similar to a driven ground rod, but it uses a pipe instead of a solid rod. This method is often preferred in areas with rocky soil or where driving a rod is not feasible. Seventhly, an auger-type ground rod can be employed. This type is a hollow ground rod with a spiral auger head. It is screwed into the ground using a power drill and can be removed more easily than a standard driven rod. Eighthly, a chemical ground rod can be considered. This rod, typically copper-coated or galvanized steel, is driven into the ground and surrounded by a chemical backfill to enhance conductivity. While relatively easy to remove, it may have a shorter lifespan compared to other methods. When choosing a method, you must consider factors such as soil conditions, site access, and local regulations. The service grounding conductor should be sized according to code requirements, adhering to standards such as those found in the National Electrical Code, NEC Table 250.166. Proper bonding and grounding connections are crucial for ensuring safety and compliance. Soil resistivity plays a significant role in the effectiveness of any grounding system. Low soil resistivity allows for better dissipation of fault current. Soil testing can determine the resistivity and guide the selection of the most appropriate grounding method. For instance, in areas with high soil resistivity, chemical ground rods or multiple ground rods in parallel might be necessary to achieve the required resistance to ground, which should typically be 25 ohms or less. The depth at which the grounding electrode is buried or driven is also important. Deeper electrodes generally encounter more stable soil conditions and moisture levels, which can improve their performance. The connection between the grounding electrode and the service grounding conductor must be robust and corrosion resistant. Exothermic welding, also known as CAD welding, provides a permanent, low-resistance connection that is less susceptible to corrosion than mechanical connections. Mechanical connections, such as ground clamps, should be made of compatible materials to prevent galvanic corrosion. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. Ground resistance testing should be performed periodically, especially after significant changes in soil conditions or electrical loads. The test measures the resistance between the grounding electrode and remote earth, providing an indication of the system's ability to dissipate fault current. In addition to the grounding electrode, proper bonding of metallic components is crucial for creating a low impedance path for fault current. Bonding involves connecting all metallic parts that could become energized during a fault, such as metal conduits, enclosures, and equipment frames. The bonding conductors should be sized according to code requirements, such as NEC Table 250.102, and securely connected to the metallic components. Surge protection devices, or SPDs, can further enhance the protection of electrical equipment from transient overvoltages caused by lightning or switching surges. SPD should be installed at the service entrance and at downstream distribution panels to provide multiple layers of protection. The grounding system provides a reference point for voltage stabilization and reduces electrical noise. A properly grounded system can improve the performance and reliability of sensitive electronic equipment. In industrial settings where large motors and other inductive loads are common, the grounding system plays a critical role in mitigating voltage sags and swells. The grounding system should be designed and installed in accordance with applicable codes and standards, such as the NEC and local electrical codes. These codes provide detailed requirements for the selection, installation, and testing of grounding electrodes, conductors, and connections. Proper documentation of the grounding system, including the location of grounding electrodes, conductor sizes, and test results, is essential for future maintenance and troubleshooting. The documentation should be kept in a readily accessible location and updated as needed. In some cases, it may be necessary to consult with a qualified electrical engineer to design and install a grounding system that meets the specific needs of the installation. An engineer can perform detailed calculations and simulations to ensure that the system will provide adequate protection under all operating conditions. The selection of the appropriate grounding method and the proper installation and maintenance of the grounding system are critical for ensuring the safety of personnel and the reliable operation of electrical equipment. Grounding is the process of creating a low-resistance path for fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. This protects people from electric shock and prevents damage to equipment. The service grounding conductor, also known as the equipment grounding conductor, is the conductor that connects the grounding electrode to the service equipment. It must be sized according to the size of the service entrance conductors, as specified in the NEC. The grounding electrode conductor is the conductor that connects the grounding electrode to the neutral bus in the service equipment. It must also be sized according to the NEC. The grounding electrode system consists of all the grounding electrodes that are connected together to form a single grounding system. The grounding electrode system must be capable of carrying the maximum fault current that could flow in the system. In addition to the grounding electrode system, there are other grounding requirements that must be met, such as bonding all metallic parts that could become energized during a fault. This includes metal conduits, enclosures, and equipment frames. Bonding helps to create a low impedance path for fault current, which helps to trip the circuit breaker or fuse quickly. There are also requirements for grounding sensitive electronic equipment. Sensitive electronic equipment can be damaged by voltage surges and electrical noise. A properly grounded system can help to protect this equipment. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. Ground resistance testing should be performed to verify that the resistance to ground is within acceptable limits. Visual inspections should be performed to check for loose connections, corrosion, and other signs of damage. If any problems are found, they should be corrected immediately. The grounding system is an essential part of any electrical system. Proper grounding helps to protect people from electric shock, prevent damage to equipment, and improve the performance of sensitive electronic equipment. Understanding the different methods of service grounding, along with proper installation and maintenance, is crucial for ensuring a safe and reliable electrical system. Always consult with a qualified electrician or electrical engineer for specific grounding requirements and to ensure compliance with local codes and regulations. Furthermore, consider the impact of lightning protection systems on the overall grounding strategy. Lightning protection systems often require dedicated grounding electrodes and bonding to the main grounding system to effectively dissipate lightning strikes. The integration of lightning protection grounding with the service grounding system should be carefully planned to avoid creating ground loops or other potential hazards. In addition to the methods already mentioned, alternative grounding techniques may be required in specific situations, such as when dealing with underground distribution systems or hazardous locations. These techniques may involve the use of specialized grounding electrodes, such as exothermic welded connections to underground metallic structures, or the implementation of intrinsically safe grounding systems in hazardous areas. The choice of grounding method should also take into account the long-term maintenance and reliability of the system. Some grounding methods may require more frequent inspection and maintenance than others, depending on the environmental conditions and the materials used. For example, grounding electrodes installed in corrosive soils may need to be inspected more frequently for corrosion and replaced as needed. The design and installation of a grounding system should be a collaborative effort between electrical engineers, contractors, and facility owners. Open communication and clear documentation are essential for ensuring that the system meets the needs of the facility and complies with all applicable codes and standards. Regular training and education for electrical personnel are also important for maintaining a safe and reliable grounding system. Electrical personnel should be trained in the proper methods for inspecting, testing, and maintaining grounding systems, as well as the potential hazards associated with improper grounding. By following these best practices, you can help to ensure that your electrical system is properly grounded and that your facility is protected from the hazards of electrical shock and equipment damage. The cost of implementing different grounding methods can vary significantly depending on the materials used, the labor required, and the complexity of the installation. When selecting a grounding method, it is important to consider the total cost of ownership, including the initial installation costs, as well as the ongoing maintenance and inspection costs. In some cases, it may be more cost-effective to invest in a more expensive grounding method that requires less maintenance over the long term. The size and type of grounding conductors should be selected based on the size of the service entrance conductors and the potential fault current that could flow in the system. The NEC provides detailed tables and guidelines for sizing grounding conductors. It is important to consult these tables and guidelines to ensure that the grounding conductors are adequately sized to handle the maximum fault current. The grounding system should be designed to minimize the impedance of the ground fault path. A low impedance ground fault path helps to ensure that fault current will flow quickly and trip the circuit breaker or fuse, de-energizing the circuit. The impedance of the ground fault path can be reduced by using larger grounding conductors, minimizing the length of the grounding conductors, and making sure that all connections are tight and corrosion-free. The grounding system should be designed to prevent the flow of objectionable current. Objectionable current is current that flows on the grounding conductors under normal operating conditions. Objectionable current can cause nuisance tripping of circuit breakers and can also create a safety hazard. The flow of objectionable current can be prevented by properly bonding all metallic parts, using isolated ground receptacles for sensitive electronic equipment, and avoiding the creation of ground loops. The grounding system should be designed to protect sensitive electronic equipment from voltage surges and electrical noise. Voltage surges and electrical noise can damage sensitive electronic equipment and can also cause data corruption. The grounding system can help to protect sensitive electronic equipment by providing a low impedance path for surge current to flow to ground. Surge protective devices, SPDs, can also be used to protect sensitive electronic equipment from voltage surges. The grounding system should be designed to comply with all applicable codes and standards. The NEC provides detailed requirements for the design and installation of grounding systems. It is important to consult the NEC and local electrical codes to ensure that the grounding system complies with all applicable requirements. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. Ground resistance testing should be performed to verify that the resistance to ground is within acceptable limits. Visual inspections should be performed to check for loose connections, corrosion, and other signs of damage. If any problems are found, they should be corrected immediately.